All right, so now we're going to talk about the atmosphere itself. We're going to talk about the composition a little bit, and then we're going to talk about the structure of the atmosphere. So the atmosphere itself is going to be a thin gaseous envelope that surrounds the Earth. So you might know that already, but I figured I'd remind you. So this picture right here kind of shows you the atmosphere to the best of our understanding. It is hard to tell how far the atmosphere really goes. And at certain parts, it's a little bit further than others. It's not a perfect, depth above the surface or height above the surface that we know. Okay? So the atmosphere has gas molecules that are suspended particles of either solid or liquid, as you may know. And if they are solid or liquid, they're going to be falling precipitation, right? As falling precipitation. So the atmosphere is also going to be responsible for heat trapping, which allows us to actually survive in this world. Otherwise, we would be so cold that it would not be habitable. So, yeah, it would not be habitable. Give me a second, my dog wants out. About that. Okay. So the atmosphere is going to cause the weather that we experience every day. That is pretty plain, and it is mainly composed out of nitrogen. So if you remember from chapter 12, nitrogen was about, I think, 72 or 75% of the atmosphere. Also oxygen as the second most common element, and then other smaller trace elements. Among those were the molecules that we know as greenhouse gases. So remember that although they weren't very large amounts, like on the order of 0.000%, I think, they are increasing and they have a very large effect on the current weather and climate as we're seeing them throughout the decades. So I'm not going to go in depth about the composition because we saw this in chapter 12. So if you need a reminder of it, go back to those slides and check them out. Okay. A term to have in mind is going to be relative humidity, and you're going to have to do a few exercises on relative humidity for your lab this week. So relative humidity is going to be the moisture that there is for the possible amount that could be felt for the given temperature. Okay, so that's kind of a mouthful, but basically, depending on where you are, is the amount of moisture that can be felt with the temperature that you're at. So that will become pretty clear to you when you do the exercise on this week's lab, so definitely check it out. So again, this humidity is going to be a major player in the amount of water vapor that you have in the atmosphere, right? So it increases during the night because of cooler temperatures, and it will decrease during the day as the day goes on towards warmer temperatures. So in the afternoon is going to be the driest overall, and then early, like dawn time, is going to be the more moist for most locations. So virtually all water vapor comes from the evaporation of water from Earth's atmosphere and the various parts of the Earth, right? So seas, rivers, lakes, evapotranspiration, all of that has to do with the amount of water vapor that we have. So later on, this water vapor will condensate and fall as precipitation, and eventually it will evaporate again, making it, an ongoing cycle. So that's part of the water cycle that we have already seen. And if you need to review the water cycle, we covered it in chapter 1, and I think it was chapter 6 on flooding. I think it was 6, yeah. So again, if you need a reminder, check those out to see what the hydrologic cycle looked like. Now we're going to talk about the structure of the atmosphere itself. So I think I covered it slightly. I think it was also in chapter 12. But now we're going to go in a little bit more depth. And you're actually going to go in further depth for your discussion board, I think, discussion board 15 this week. Okay, so as I was saying before, it is actually kind of hard to tell the limits of the atmosphere at high altitudes, and they vary from place to place. So we know that it is very thin overall compared to the overall size of the Earth, but we don't know necessarily if it goes, as the image is showing you, 90 miles above the Earth's surface, or maybe just 85, or maybe 95. It is hard to tell, and it varies from place to place. So it is, as you see in the slide itself, most of the gas molecules that are formed within the atmosphere fall in the first 100 kilometers. Okay, so 100 kilometers is going to be the first 60 miles. So most of those gas molecules are going to be composed in the first three major layers of the atmosphere, and then a few of them are going to fall in the topmost layer of the atmosphere. So it's split into four major layers. The bottom one is going to be called the troposphere, which is where most things that we know are ongoing. Then the stratosphere, then the mesosphere, and then the thermosphere. So you're seeing that in the picture, at least, you're seeing that the troposphere is divided from the stratosphere by this kind of line that we call the tropopause. Then the stratosphere is going to be divided from the mesosphere by the stratopause. And then, as you might have guessed, the mesosphere is going to be divided from the thermosphere by the mesopause. Okay, so a pause is going to be that line splitting them up. And then it's going to be named after whatever layer it is above from. Sounds funny, but yeah. So in the book, and as you will see in the discussion board in the book, mostly only the troposphere is covered. So I'm going to go through it, and then you and your discussion board will tell me a little bit more about the other three layers of the of the atmosphere. One thing to take into account is the shift in temperature as you're seeing in the graph. So you're seeing that, and that we experience, that as you get higher in altitude in the troposphere, the temperatures decrease pretty rapidly. And then once you get into the stratosphere, the opposite effect takes place. Maybe not as rapidly, but you see that the temperatures actually build up. Then in the mesosphere, they go back down, also not as steeply as in the troposphere. And then in the thermosphere, they go incredibly high. Okay? So that's something to take into account. Another thing to know is, or see at least, is that you see that the aurora borealis and aurora australis usually happen at heights of very high, somewhere between, 65 miles and further up into the atmosphere. So that's another question on your discussion board. Of course, you're supposed to do a little bit more reading than just what I told you. But again, look at the graph. That's a clue. All right. So the troposphere itself, as you're seeing, there's a rapid decrease, as I mentioned. This results from the air pressure that is decreasing, right? So the higher up in altitude that you are, the less pressure, the less pressure that you have. So it's harder for us to breathe that air, for example. So people who were born in higher altitudes are actually better, if you would, at accommodating to hard breathing conditions. So me, I, for example, was born in about 8,000 feet altitude and was raised in that altitude for the first 17 years of my life. So I almost never notice, being hard of breath when I'm working out or when I'm hiking or whatever it may be, because I'm used to not having as much air. For example, people who are born at sea level experience the opposite effect, because usually they were born in a place where they had a lot of air, so they did not have to, or their lungs didn't have to work as hard for it. So with this decrease in pressure, there's also abundant water vapor in the form of cloud development. Okay, so that's something important to have in mind. So most of the cloud development happens in the troposphere. All right, so pretty much everything that we have in terms of cloud cover is going to be in the troposphere, below the tropopause, which is pretty much the highest point at which any cloud cover reaches. So we have a few different types of clouds, but right now we're just going to go through two basic ones. You may go through the rest on your own if you're curious. So cumulus is going to be perhaps the name that you guys are familiar with, or stratocumulus. So those are going to be those puffy, kind of fair weather clouds that kids paint, or are painted in kind of comical or cartoonish like movies or shows. They're going to be the cumulonimbus. Those are going to be thunderstorm developing clouds. They usually have a vertical development, so they're going to be very large kind of columns that flow upwards, And usually the top of those cumulonimbus clouds tends to be the tropopause. Okay? So in this cumulonimbus type of cloud, you have latent heat that is being released as you go from water vapor into liquid water in precipitation. So it is usually in cumulonimbus cloud formation where you get precipitation undergoing. So you have latent heat released, again, because you go through condensation processes. So that's something to also keep in mind. So, so most of the greenhouse gases also lie within the troposphere, as we know. And the only thing that I guess doesn't really happen that affects us directly in the troposphere is going to be the ozone layer, if you would, the maximum amount of ozone that we experience. That maximum amount of ozone actually happens in the stratosphere, sorry. As you're seeing here in the figure, you're seeing that the maximum ozone is actually in the stratosphere about 15 miles above the surface for the most part. So, again, you'll have to cover it, but later on you'll have to see the stratosphere, mesosphere, and thermosphere with a little bit more detail in order for you to complete discussion board number 15. From now on, we get a little bit more into meteorology, which I am not an expert in. So I'm going to try to do my best to explain it to you, but if you need more references, your book does a really good job at explaining it, and I'm sure that online you can find good resources as well. Or just ask me, I might be better at explaining it through writing. So again, we're going to go through atmospheric pressure and circulation a little bit, okay? So atmospheric pressure, or also called barometric pressure, or also called air pressure, is going to be the weight of a column of air that is above any given point. So another way to think about it is going to be basically a force that is exerted by the gas molecules on a surface. Okay, a force that is exerted by the gas molecules on the surface. So you might know this, but there is less pressure the higher in altitude that you get. So this is because basically there are less gas molecules the further from the surface that you get. So you may have noticed this particular phenomenon as you are changing pressure. Maybe you're driving up a mountain and you see or you feel that your ears are popping. It's because the pressure is decreasing, or the same thing happens when you're driving down it. The pressure is increasing, so your ears are also going to pop. So that is actually another reason why, for example, in airplanes you hear a lot of babies crying more so than other times, is because in the airplane itself the pressure is set at, I think it's 8,000 feet or so, and so it's higher than most, or sorry, lower than most of the pressures that they're used to feeling. So a trick to have them be comfortable with the pressure and that the ears don't hurt is to actually pour like physiological liquid on their nose, so that way that opens up the airway through the whole system. So just a trick if you have kids or know of people who have kids and just hate traveling on airplanes, that's a trick to get them to at least feel comfortable with that part of the trip. So cold air is going to be denser than warm air. So cold air is going to have more pressure than the warm air. So you can think about this as kind of like being the gas molecules as being kind of people, or just the pressure itself as being kind of people. So whenever it's cold outside, people want to huddle together so that they are warmer. So you can think about it the same way. So because it is colder outside, you have to have more pressure. Okay, more pressure between the bodies that are huddling together, or something of the sort. So I'm going to pause the video so I can explain to you the figure on the left on the next short video, because it's going to be a little bit long.